Hi everyone, thanks for taking time to attend this talk. My name is Jin Song. Today I want to share you some internals and challenges of Flink SQL and to explain the challenges to build a streaming SQL engine and what is Flink SQL engine. So first, introduce myself. I have worked at Alibaba for nearly 9 years, mainly focused on streaming batch storage for big data. Now I am a staff engineer in Alibaba and is also the leader of lake storage team of several people. Before this, I participated in several communities. I'm also a PMC member of Apache Flink and a committer of Beam and Iceberg. Currently, I have created a lake storage named Apache Payment. It is a new lake format focused on streaming, formerly known as Flink Table Store. So next, I will. So here is the agenda. This year is 2023. Flink SQL has gone through many years of development and is already a very stable, stable streaming SQL. So first of all, I would like to introduce the main scenarios of Flink SQL. What is the main problem it solved? Second part, what are the challenges of latest Flink SQL? And third, let's talk about the new progress in state and storage combined with Flink SQL. And finally, summary and futures. So let's take a look to what is Flink SQL. There are three main scenarios for Flink SQL, and I probably know more about Chinese companies. One of the main scenarios is that data movement, because Flink SQL has a streaming batch of data movement experience and has a strong connector ecosystem and has a rich function support and lookup join and other SQL functions, so that the data movement can be a lightweight processing. And the second scenario is that streaming processing in data warehouse. You have maybe every company has offline data warehouse. Use Flink SQL, you can accelerate the data processing to streaming data warehouse. And it can handle some complex processing, not just data movement. It can do aggregation, unbounded aggregation. It can do streaming join. You can compute a page view or user view. Yeah. So including aggregation group by, over aggregation, and so on to accelerate in the data warehouse and make the ATL to seconds level latency, not just by days. The third is data driven, is event driven. The scenario I do not introduce more. It is more dependent on Flink SQL, like some window aggregation and CEP and so on. In usual case, maybe a risk control, a monitor, alarm. So first, I want to introduce the connector ecosystem of Flink SQL. Flink SQL has a strong connector ecosystem, which means it can be used as a good movement underlying framework. I figure you can take a look at the picture. Flink SQL and Flink CDC supports a large number of connectors, and the native support for the concept of changelog, so that the database CDC state, such as MySQL binlog or from PostgreSQL, can be very easy to use Flink to streaming read. And the follow-up will also mention changelog support. So there at least in China, there are a lot of companies based on Flink SQL to build data movement stream batch unified system. This have very good experience because Flink has a very strong ecosystem. It has many connectors. People can launch a streaming long-running data movement job and can launch a one-time batch job too. And in the data movement, it is not just a data movement. You can use some SQL projection, filter, and SQL functions. You can also use user-defined functions. And even more, you can use a streaming lookup join. You can lookup join from database or something key value store, which is very convenient. It is worth mentioning that the general batch of data movement using is you can use a Flink session cluster. Why? Because long-running Flink cluster, which can make small data movement become super fast. For example, 10,000 records movement only needs seconds of time. Scheduling time consuming is very short. And we just talk about the connectors. So here is a deep dive to SQL parsing and execution. Yeah, this picture, this is a high-level overview of how Flink SQL works. Flink SQL supports SQL and table API as public relation API. Table API also supports Java, Scala, and Python. You can use Python Flink too. Flink has an internal representation of user program called logical plan. I think many systems has this logical plan too. Flink will convert the public API into those logical plans. The conversion will involve a catalog. You can see in the figure. Catalog will help to look some metadata information and resolve functions and resolve table paths. Yeah, it can have metastore or user-defined catalogs. Yeah, Hive catalog is the only in open source is the only persistent catalog in open source. Yeah, and I think there should be a Confluent registry catalog too, but this is not ready in open source. Logical plan is a start point of optimization. It represents a logical computation on the data set without worrying about the execution details. So next, the Flink will do lots of different optimization rules. Yeah, the Flink's optimizer will convert initial logical plan into an optimized physical plan. Yeah. And then, and finally, through Flink SQL's code generation and some optimized, the physical plan will be translated to an internal streaming API under data streaming. It is the lowest API of Flink. Yeah. And there are a code generation to generate binary data. It has very high performance throughput, yeah, and have state-of-the-art operators, and have fine-grained resource optimizations. At last, transformations will be converted into job graph, which is ready to be executed, and then job graph will be submitted to Flink cluster, just like from to Yarn to Kubernetes and clusters. So this is a very rough overview how Flink SQL works. Next, I will give an example to explain the workflow. In the left-hand side, it is a simple join query. Yeah, joins T1 and T2 with a condition. In the right hand, it is a parsed initial logical plan. Yeah, you can say T1 and T2 is parsed into scan nodes, and then join operation is parsed into join node, and where clause is parsed into filter node. Yeah, and selected clause is passed into project load. Then that they all represent a specific data operations described how to generate a new dataset format input dataset. Yeah. The logical plan will be sent into optimizer and to physical plan and to transformation and to be a job graph and submitted to cluster. So this is how Flink SQL works. Yeah, so we know how Flink SQL works, but the most important contribution of Flink SQL is changelog mechanism. Changelog is not a new concept invented by Flink SQL. In the relation database world, MySQL uses a well-known bin log, a binary log, to represent changelog to record all modification operations into database, includes insert, update, and delete operations. Similarly, a changelog in Flink SQL is also used to record these data changes in order to achieve incremental data processing. With the changelog, every record has a metadata represent what is change operation of this word. It can be insert, it can be update, it can be delete. Yeah, the source will emit. For example, you can take the figure. The source will emit two insertion records, hello and word. The first aggregation will accumulate them and emit two insertion records. You can say hello 1 and word count 1. So the frequency of count 1 is too low. And another hello word coming in. Yeah, the first aggregation will update the count of hello to from 1 to 2. So this is an upgrade operation. Yeah, in many database binlog systems, they will track update operation into two records, updated before and updated after. Yeah, so in Flink SQL, the same. The update will be translated to one update before to retract all the values and a new update after, yeah, to update the value. So when the update before arrives the second aggregation, you can hear it will first do retraction for this word to minus the frequency from 2 to 1. And when update after arrives the second aggregation, it will do accumulation for this word. Insert count 2, frequency 1 into the result table. So as you see, with changelog mechanism, the final result is correct. The update before is retraction. So that's why we need changelog. But a lot of all case, aggregation don't send or update before. If your sync is absurd sync, it does not need update before. Flink SQL will optimize this situation. So I have explained how Flink SQL works and what is changelog. So this is a business example. Yeah, for example, you need to synchronize the data of a business database and complement the user's information, user fields. Yeah, after some simple processing, write into DynamoDB for some analytic task query. With Flink SQL, you can just use the SQL as above. It is very simple, completely transparent. You don't need to say CDC changelog related concepts. You just need to write a business SQL. First, read the CDC data of the orders table, ensuring that its updates are also synchronize the data stream downstream. And second, use Flink SQL's lookup join to add customs fields based on customer ID. And third, write the data to DynamoDB. The case is very simple. You don't need, say, cd changelog, some related concept. You just need to write a SQL. So the first part, the above give a general overview of what Flink SQL can do and what general principles are. So this section will describe what the challenges of Flink SQL are. This section is more in depth. So first challenge, for example, you need to compute statistical values for per day of data. It is often true that this data will a bit late, sometimes up to several hours late due to some upstream system failures. So the streaming system creates some concepts like a window. You can say streaming window to define the scope of aggregation, trigger to define the output timers, and also you need to define specific handling of late data, which can be a bit complicated. But real-world data statistics are often hours or day levels. So long time computation, we don't not use the complicated window. We just can write a streaming batch unified SQL. Yeah, you can take a look to just select some from T group by corner. So let's take a simple aggregation query as an example. In this case, you can just use a simple group by low window, and the result will be output every time, and will change it every time. So we need an abstract sync too. Maybe this abstract sync is a DynamoDB. What is abstract sync? Yeah, the sync, the store of the sync can update data by some primary key. You can define a primary key, and you can update by primary key. So this sync is an abstract sync. For example, some DynamoDB or Redis or Cassandra or HBase. Yeah, or you can use some traditional relational database. We often say that Flink SQL is the exactly correct result, not just at least one. But how can it be output early and correct? Because if you can configure a checkpoint interval to 3 minutes, but the date latency will be very earlier, just like one second. You output it early, and it should be at least once. But Flink SQL can do exactly once. Yeah, it should not be, because the early result should not be the final result. It can be wrong. But the underlying principle is that to rely on idempotency for the achieving final consistency. So early data will be wrong. So then finally, yeah, the correct results will be overwrite, upstart the same primary key. Yeah, you can use this case to understand what is the common case of Flink. But it is not over yet. There is a problem in this mode. And you might have guessed the state will be bigger and bigger. And one day the performance will not work and the state will boom. Yeah, so what to do? You need to define state time to live to keep only the most recent data. This is very tricky. So it requires you to have a precise judgment of the business. You will define a precise time to leave time. Late data should not be later than the time to leave time. Otherwise, it may lead to some overwriting of the wrong data, leading to a very serious consequences. Yeah, this may also be a serious problem with current streaming computation. Streaming computation is not that correct. Eventually, you need to do a batch computation as the source of truth results to override streaming computation results on the next day, maybe. So next challenge, let's go to next challenge. Next challenge is the problem of retraction amplification. Yeah, what is a retraction amplification? We previously talked about how Flink SQL's changelog solves the update problem as a root of streaming computation. Let's recall that the data is divided to 4 types: insert, update before, update after, and delete. Yeah, for example, if one piece of data comes to updated, it will output corresponding 2 records with update before and update after. So what's the problem? Here will lead to application of number of data records. You can see the example. The example has one join, one left join, and another one left join, and aggregation. Yeah, so think about the complex cycle. In this example, when you join twice between aggregation, if one record from T2, yeah, the left join load will output 2 records, one update before and one update after. And then the next left join will output 4 records, 2 update before and 2 update after. And the aggregation will output 8 records, 4 update before and 4 update after. Yeah. You will find a small amount of data triggered a lot of computation, consuming a lot of machine resources. So how to resolve this problem? So I think you can use mini-batch to resolve this problem. Yeah, what is mini-batch processing? Instead of doing the calculation for each record, the default model of Flink SQL is calculation for each record. Yeah, instead of it, mini-batch will actually buffer the records into some heap memory to hold the bundle. And there are 2 triggers to trigger the bundle calculation. One is time limit. If I defined a 10 seconds mini-batch, the data will output max 10 seconds. The other is size limit. If you defined 4,000 records, one batch, yeah, you can also use both. When the bundle is triggered, Flink will not aggregate the buffered records into a single accumulator for each key and merge this accumulator with 1 in state. So this will reduce the output amount and reduce downstream nodes. The application of data will be reduced because for single key, multiple records, multiple updates before, update after will be reduced to 1. Yeah, and more, there is only 1 state accessing per key, so for many buffered records. So the state accessing cost will be reduced too. Midi-batch has better performance. So I think if your scenario can be applied, midi-batch should be opened always. But currently, Flink SQL still lacks midi-batch implementation for streaming join. Yeah, it has some difficulty, but it should be done. And it is deserved to be done. So I think in Flink 2.0, midi-batch join will be ready. As I said, changelog is split roughly 4 types. Yeah, this is another challenge. Update is split into update before and update after. Essentially, this is due to distributed processing. And here is an example to show a scenario where composite update events has to be split into delete and insert, just update before and update after. Yeah. So assuming that changelog of the record with, yeah, you can see the figure. Yeah, if you say that record with ID equal ID1 in source table, S1 is at time T0, it will output ID1 and level 10. Yeah, and then time T1, the row is updated to ID1 and level 20. Yeah, this corresponds to 3 split events. The first event is insert ID1 level 10, and the second record is update before ID1 level 10, and another update after ID1 level 20. So look at the SQL statement in example. The primary key of source table S1 is ID, but the join operation leads to shuffled by column level. Yeah. In this example, if the join operator runs a parallelism of 2, the above 3 events could be sent to 2 tasks. So in this case, even if composite update events are used, they still lead to split in order to be shuffled, because the join should be shuffled by join key to different tasks for parallelism processing. So in a distributed environment, the actual join is processed in parallelism on 2 tasks. So the sequence of the events received by downstreaming operator, yeah, in this figure, a sync task in this case, has a few properties as indicated at the bottom of the figure. Yeah, while the sequence of events is same as the one in sequential processing. So if the downstreaming operator does not take out of orderness into account in its implementation, yeah, it may lead to incorrect results. For example, if the primary key declared by the sync table is ID and the external storage is updated by upsert, without additional countermeasures, the row with ID1 will be deleted from external storage. And yeah, you cannot find this ID1 record. Yeah, results, wrong results. So how to solve this problem? Yeah, in the open source Flink SQL, we introduce the sync upsert materials to solve this problem. Sync upsert materializer maintain a list of raw data in its state. And when a row enters its operator, depends on whether it is an add or retract event, it checks its internal state for its row based on the deduced upsert key or entire row if the abstract key is empty. So in this way, and finally, it emits the changelog events based on the primary key of sync table. And the source code of sync material, abstract materials for you can see in open source. The figure below shows how output changelog events from join operator are processed and transformed into input changelog events of sync table. In the second scenario, when a row removed from state is the last row, it will emit the second last row downstreaming. So in the third scenario, when update after is processed, single abstract materials will emit it as it is. So we introduce this sync abstract materials to correct the orderness of upstreaming changelog. So it should be work for small data. So do we happy now? No, because sync abstract materials maintains a list of raw data in its state. Potentially, this can lead to a large state size. So the state will be larger and larger, and the Flink SQL streaming job will not work. Therefore, we should try to avoid using it as possible. So, and you need to define a state time to live too in this scenario, because and if you define a smaller or too smaller state time to live, and the results will be incorrect. So we can just So another way, you can just use RocksDB inside checkpoint. Actually, in open source, we use state backend as the sync abstract materials. But in many cases, maybe we don't need to use state backend. We can just use a single RocksDB. Think about it, Flink has a global checkpoint that aligns all tasks. So the data within a checkpoint is distributed by and disordered, and the data between checkpoints is distributed and strictly ordered. So in this case, without open, you can just use a RocksDB in the checkpoint to adjust this orderness and finally clear all data in this checkpoint, and then in next checkpoint, you can use a new RocksDB. So this optimization is still ongoing in public, in open source Flink. So last problem is Nondeterminism. In streaming mode, if you are using current time step and allow, that will change over time. It is good for append-only data, but for changelog, if you use this function, that will output wrong changelog, because previously the current time step is low, and then update before computation for update before will be wrong. So I want to explain this because all operations that lead to generate incremental messages that maintain complete internal state data. And the operation of the entire query pipeline relies on the guarantee of correct delivery of update messages between operators which can be broken by non-determinism, lead to errors. Yeah. So you can take a look to this picture. If you read a CDC source, changelog source, from maybe MySQL, maybe a PostgreSQL, changelog, CDC, and use no non-determinable SQL, for example, lookup join, because lookup join is also a non-deterministic operator, because this time you lookup join from just one field, and next time maybe you will lookup join another field, yeah, another value, includes current time step, and they will output the results to and in this picture, the result will be sent to aggregation group by and have a sum. Due to non-determinism, yeah, sum may be incorrect because retractions output different records. Yeah. For example, if a previous record joined 10 value and then joined 15 value, yeah, the sum will be subtract an additional 5. Yeah, so the changelog relies on us to generate reliable retraction. So how to solve this problem? The most intuitive way is get around it, and you can just not use the non-determined operators. Another solution is simple too, and you mean in streaming world, the all value are not reliable, but you can do a streaming deduplication. Maybe you can just use Flink state. Yeah, of course it will. When you do this deduplication, the output of the deduplication will be correct. Yeah, whatever the non-determined functions or non-lookup join. Yeah, of course it will materialize the whole table. Yeah, perhaps not so cost effective. You can also consider use an external system to complete this deduplication. Yeah, this external system needs to be able to deduplicate and generate a changelog. Yeah, you can choose Apache payment if your latency can accept 1 minute. So actually in the streaming world, streaming deduplication is very normal and common. Yeah, you may, if you want better correct results, maybe you will do many deduplication. So at the last, the challenges are above. At last, I will give a forward look into state and storage. We've mentioned the state-related issue many times before. The state has time to live. Flink has been successful before because of state, but now state has surfaced a lot of issues as well. So we can take a look to the picture. This is the architecture of Flink state. The core design of Flink state is local state. Because of local state, Flink has a very powerful, a very high performance throughput. You can see in the picture, each task has own local state. All files are in local. Flink will checkpoint state files into distributed file system with incrementally and async. This is for failover recovery. Yeah, Flink state, local state has high performance. If not a large amount of data, it has very high performance. Yeah, because nothing can outperform a local RocksDB. Yeah, I think RocksDB is very successful and It has very high performance KV lookup. But for bigger state, maybe your state bigger and bigger, you find the performance is better and better. Yeah, you need to rescale. If you have 10 tasks to run Flink SQL, and then you may lead 20 tasks, yeah, you need to rescale, use more and more resource. Or you need to configure state time to live. State time to live will bring other problems, like the result may be not correct. So, and then for this problem, you cannot just use Flink local state. You cannot just use local RocksDB. You can use external state backend. For example, you can implement a DynamoDB state backend, or you can implement HBase or Cassandra state backend. Yeah, this can also solve problems, but the state and the state can be shared by multiple stream jobs. But you need to pay for key value service. It should be very expensive. And next, I will discuss you about this aggregated state. This may be ready in Flink 2.0. So in Flink 2.0, the community plan to improve the state architecture. Of course, this aggregated state, maybe you load a Rockset or RocksCloud. RocksDB can maintain partial files in local and all files in distributed file system. So on the top of RocksDB, we can also build this aggregated state architecture too. And then we expect hot files are in local, and the code files are in the distributed file system. This should be very suitable for big states. This sounds very good, but there are many challenges. Yeah. For example, how to cut data, because maybe all files are hot files, and the performance will be very bad. And how to rescale, because Flink has done many features to how to scale state from 10 tasks to 20 tasks, for example, and how to share. For this aggregated state in Flink 2.0, we want this state can be shared by multiple tasks. Yeah, there are problems, and we don't know. Yeah, the things still be researched. And the third way, yes, you can also don't use Flink state. You can use something other like lake state, maybe Apache payment. It provides minute level latency, and replace state. You can use some merge engine of Apache payment. It acts just like something like a ClickHouse, of course, lake version. You can use it as a deduplication, partial update, aggregation, first row, and it has no date time to live. Its performance improvement is very good, yeah. But you need to modify your Flink SQL. So at last, I will give you a short summary. Yeah. Summary, Flink first, I just introduced Flink SQL, the scenarios of Flink SQL, data movement, data warehouse, and event-driven. And then I introduced the core concept of Flink SQL is changelog. All things, all features are built on changelog. And the real case of data movement, and then I introduced 4 challenges of Flink SQL. Late data, unbounded, we are using unbounded operators. We use a mini batch to resolve retraction application, and even the ordering and the long determinism. And last, I just introduced the state of Flink SQL. We have planned to improve it in Flink 2.0. Thank you, everyone. Thank you for listening.